All right, folks, I'm going to get into some related rates. Now, these are another version of some problem solving, a lot like optimization. I mean, they have their own twists and quirks to them. I'm not sure which one I like more. I might like the related rates more. They're they're both pretty interesting. Related rates kind of deals with a different sort of calculus method, I guess, than optimization. Optimization, you are just defining a function as a single variable and looking for local mins and maxes and then comparing them to boundaries. So basically, it's a lot like graphing. Related rates are not. So related rates are instead going to involve a lot of implicit differentiation is the biggest thing. So it's very rare actually that you will have something that you're taking a derivative with you won't really have a question where you take a derivative with respect to a variable that it's written in, and that be kind of like the only thing that you're doing. So it's built quite a bit differently, but we'll see that as we go forward. So a lot of times in math, we're asked to solve problems where, well, maybe not in math because at this point you haven't really done them. But a lot of times in introductory calculus, once you get to this related rate section, you realize that there are problems that are out there that exist where you know some speeds or some rates of change of things, and you might know the speed of one thing, and you know that it affects another. So for instance, let's talk about some of the examples where this may come into play, where you can tell that things are changing at different rates, but those rates are in fact related. So if I were filling a bucket of water, let's say you have a hose that fills it up a particular flow rate out of the hose, so there's a particular volume per minute or whatever the case may be. And so the bucket fills up. So the volume of the bucket is changing at the same rate as the flow coming out of the hose, but the height of water in the bucket changes too. And so if the bucket is very, I don't even know, I was going to say wide versus narrow. I don't know if that makes sense. But if the base of it is very small and it's built in a way where it kind of maintains that. It's maybe just a cylinder, but it doesn't have to be. It could be a partial cone or something like that. So if it was very, very small on the bottom, then the height's going to change quite quickly. But if you have a bucket that's instead like a big rain barrel or a big, any sort of large container, then with that same amount of flow, the volume is going to be changing at the exact same rate, but the height of water inside of that container is going to be changing at a much different rate. It's going to be much slower if you have something that's very large in terms of its surface area on the bottom. Same thing, snowball rolling down a hill, so the radius is changing, but the volume of that snowball is also changing. You could do like radius versus the, I don't know if it's a sphere. You can talk about a circumference, I guess, too. Usually used in a two-dimensional circle, but the circumference of the cross section, if you wish to be careful about the way we're saying things there. And then the last example that I have there, a spill. So you just got some oil spilling on the ground. And then as it spills, you have a surface area and a radius there that would be related. So again, in all these cases, these are not unrelated quantities. So that's the whole idea of calling these things related rates, because you can't, in the case of a snowball, expect to have an increase in radius without having an increase in volume. That just doesn't make sense, especially if we make some sort of constraint where we know it has to be spherical. But if you double the radius, that does not mean that the volume is doubled. In fact, it probably means something quite different that we can figure out. Either by, in some cases, some logic and common sense will be able to get you where you need to go. But in other cases, calculus is very, very helpful in getting to a point where you understand how these things are set up and then what we can do in order to solve for these missing related rates. All right, so when we go through these, basically, I don't always follow these steps myself, but it's not a bad idea to kind of get into a groove of how you like to set things up and how they progress. So in this case, a lot of times if it is a problem that involves some geometry, a picture is a good idea. I'm not the best artist in the world, no close. I'm pretty bad actually, but I still will draw little sketches for myself to organize my thoughts and kind of see, oh yeah, there's some similar triangles in this problem, or okay, now this is just labeling things helps me to get my brain flowing in the right direction, I guess. List any given quantities. So sometimes they're going to tell you that the rate of change of volume in this question is 8 centimeters cubed per second. And so we will know what that is, and we should write down that we know dV by dt, the change in volume over change in time, or the derivative of volume with respect to time, is equal to, I can't even remember the number I said, plus 8 centimeters cubed per second, if that was what it was. All right, identify what you're trying to find. So it's good to have it written down like find dr by dt. So if I had dv by dt and I was doing the snowball rolling down the hill, maybe I want to know how fast the radius must have been changing for the volume to be changing at that rate that was given. So I'd be looking for dr by dt, and I'll show you how I'll write that down once I get into an example problem. So the last step there is basically you need to write an equation that has only variable quantities that you either A, know the rate of change of, or B, want to find the rate of change of. If you do not know the rate of change of it, or you do not want to find the rate of change of it, then you need to find a way to express it in a different variable. This is going to be a little more open, I guess, than optimization. In optimization, a lot of times we just knew automatically you have to express it in a single variable. That was basically what we wrote that into our list of instructions. Have to express the quantity that you want to optimize in terms of a single variable. In this case, it's quite all right to not have it expressed in terms of a single variable, and sometimes that's what you want to have. But there are times where you either need to maybe go find a rate that you don't know yet, or express one of the variables in your question in terms of a different one which you do know the rate of change of. And I can't remember if in my examples I have one that kind of flows like that, but if you come across one and you feel like you want to do a substitution, that is 100% okay. All right, so let's go ahead and take a look at what these are like. So I talked about that snowball quite a bit, so let's go ahead and do this one. All right, so we have a snowball. Again, not the world's best drawer. So we have this snowball here. If this is the center of the snowball and we go over to the edge, that would be its radius. And then the volume, of course, is the entire thing. I'm not going to kind of label that, I guess. But I will put that the volume of a sphere is 4/3 pi r cubed. All right, now, that's kind of my introductory information to this one. So I drew my picture. It's not really a given quantity, but it's an important equation. Now, technically, I guess this kind of comes up in part 4, but I was just thinking it. So again, it's a guideline. It's not the way you should do the problem. Step 1, 2, 3, 4. Just feel free to get in a groove, and as long as you're comfortable with how you want to progress, that's good. All right, so in this case, I do have that the radius is changing at a rate of 2 centimeters per minute. So that is a change in radius during some time period. That is dr by dt. That is not r prime, unless you have defined r as being some function of t. But at the time being, I just kind of have this floating concept of radius. So Leibniz notation is going to be very important during related rates, because a lot of the time it's not going to be, you're going to be doing rates that are not with respect to the quantities directly, I guess. So I'm not doing a rate of change of radius with respect to the radius, or rate of change of volume with respect to the volume. I mean, or with respect to the radius. I'm going to do it with respect to time in this case because of the minutes that are coming up here. So it's easiest to be very clear about what's going on by using Leibniz notation. So I have dr by dt. So dr by dt is equal to, and I am actually going to put, now the plus is 100% not required here. So plus and minus, and that's more bleeding into a physics realm there, where I'm worried about having some vector quantity, I suppose. But it's a reminder for myself that I have thought that this is, actually it doesn't even say that really. I guess in my head it said that it's changing at a rate of 2 centimeters per minute. It should probably say that it's either increasing or changing at a rate of plus 2 centimeters per minute. So I'm going to say, I'm just going to put a little plus here and we'll go along with that. So the idea there is that we are having a snowball whose radius is increasing as time is going on. Every 1 minute it's growing 2 centimeters in radius. Now that does mean from side to side it's growing 4, and I mean there's all kinds of implications of that. And then the volume, what I want you to imagine is that there is a shell of volume that's getting added on. So you have the original snowball that's sitting right here, and then you're going to have a 2 centimeter all the way around shell that's being added onto it. That shell, as I said, is 2 centimeters, so it's not infinitely thin, where you're basically getting nothing added onto it in terms of a volume, or you're getting a thin surface area. This thing has, I don't know, if you, I don't even know what a good way to describe that would be, but it definitely, it has that nice, if you opened it up, it wouldn't be like crackly, it was super thin. It has some heft to it, 2 centimeters. So that is going to have a volume that's incorporated in that. So if you were to hollow out that shell and pour water into it and fill it all up, that water would have a very particular volume that would be able to be held in there. All right, so in this problem, that's what we're given. And we want to find the rate of change of the volume specifically when the radius is 3. So if you imagine when the radius is 3, then if we look at the instantaneous rate of change of volume, if we were to add on a shell at that point by going an extra minute, that shell is going to be pretty small because we're sitting at 3 centimeters of radius. But if we had already 10 centimeters of radius and then we went for another minute, and you get that same 2 centimeter thickness shell, that shell is much bigger because it goes around the 10 centimeter snowball as opposed to just a 3 centimeter snowball. So the moment when this rate is happening is very important as well to the how large this quantity is going to be in the very end. So the way that I write this is I am looking for, so the quantity that I want is the rate of change of volume so this is a constraint or a particular piece of information that I must follow while finding this. So dV by dt at a radius, so r, of 3. And I probably should put centimeters. Sometimes I'm a little bit sloppy in my mid-steps and I don't deal with units, and I just kind of chuck them on at the end. I will accept things like that as long as your units are okay in the end. I had a professor that made sure that we were aware of doing unit analysis as one of the better ways to self-check as you go through a problem. So if you're properly applying your operations on your units are almost like a secondary checks and balances type system where you can catch maybe mistakes that have happened if you notice, oh, this is supposed to be a volume and I got centimeters squared. That doesn't make any sense. What happened? And you can backtrack and look for it. All right, so that is equal to big old question mark, and that's what we're looking for. So I have the thing that I want, which is dV by dt. I have the quantity that we've been given, which is dr by dt. And actually, I kind of cheated a little bit earlier, and I wrote down this equation up here. which is volume is equal to 4/3 pi r cubed. dv by dt, we have a v in this equation. dr by dt, we have an r in this equation. There are no other variables in this equation. This equation, actually the way that it is the perfect equation to relate the rate of change of volume with the rate of change of the radius. So we're going to take that, and I'm going to just rewrite it down here as v is equal to 4/3 pi r cubed. So how do we get rate of change with respect to time? Well, we take a t derivative. There are no t's in this equation. That is 100% okay. When we were taking x derivatives of y squared, and we said there are no x's written there explicitly, we said, well, we just gonna pretend that y is some big function. And so if it was y squared, you take the outer part, it's a function inside of a function, the square, or the y with the square happening outside of it. You take the 2, move it down to the front, leave the inside alone, multiply by the derivative of the inside. So in this case, we're basically doing the same sort of thing. So v, volume, obviously is changing as time goes on, so it's some function of t. I don't know how it's a function of t though, so I'm just going to say let's take the t derivative of v. And I'm going to write it this time very, very explicitly and slowly. And if I do that to the left-hand side, I have to also do it to the right-hand side. So I'm going to take the t derivative of 4/3 pi r cubed. And so now what we end up having down here is this idea of taking a t derivative, which is not written in there. T derivative of v is the t derivative of v. How do we write that? It's dv by dt. The t derivative of 4/3 pi r cubed is a little more complicated. So the 4/3 pi is a constant. So I'm just going to write that down out front. And then we're taking the t derivative of r cubed. This is a lot like what I just said with the y squared. So we have a function r, which is somehow dependent on time in a way that we haven't, well, kind of have stated, but not really. We're going to say no, we haven't stated yet. So we have a function inside of the cube. Take the cube, move it down to the front, so that becomes a 3 out front. We leave the inside alone. Now to the power of 2, we finish off our power rule, times the derivative of the inside, which is the t derivative of r. The t derivative of r is dr by dt. So it looks something like that as I bleed off the screen. I did that on my iPad too. I just didn't give myself enough room, which is kind of funny considering I have like a good 1.5 inches out to the left. One would think I could use that. All right, so this is it. We've solved it, except for we haven't actually developed what the rate of change of the volume is yet, because we have not plugged in what it is that we know. So dv by dt is 4/3 pi times 3. I probably could have tidied up the 4/3 and the 3, and that would have made a lot of sense to do. I didn't, so I'll do that on my next line. R squared, we are told that we want to find this quantity specifically when the r is 3. Sometimes you will be told, oh, you're finding it now when the time is 8. And so you're going to have to say, oh, but what's that mean my r is? Because I'm working with an r here. And you have to go off and solve for what your r would be at that particular time. In this case, it's very direct. So we're told that it is 3 centimeters. And so this is 3 centimeters. And again, as I said, I am a little... you know what? I'm going to do it this time. We're going to be a good person. And I'm going to put centimeters. And I'm going to square it on the outside there. And then our dr by dt is a rate of +2 centimeters per second. Look at that. I cheated over to the right a little more again, and I'm running out of room again. It's very predictable. All right, so here it is. Let's tidy it up a little bit. So we'd have finally the 3 and the 3. I have 4 pi, and then I have 3 squared. 9 times 4 gives me 36, times the 2 that's there is 72. All those are positive, so plus 72. Pi is also there. If I'm doing unit analysis, I would have centimeters squared times centimeters per second. So I would be getting centimeters cubed per second, which looks awfully good because what I'm looking to describe here is the rate of change of volume, specifically when the radius is 3 centimeters. And we would get that it's 72 pi centimeters cubed per second. So that's how fast the volume is changing at this particular point in time. So I did those, and I have this written off on this screen, but I don't know. I didn't click over to it in order to do it because it made more sense to be looking at this where you could see the quantities again. So this is a really related rates problem. We set it up, find an equation that has either things that you know the rate of change of or you want to know the rate of change of, and take implicit differentiation basically of everything that's there. Plug in the values that you know, solve for the thing that you don't. In this case, it was already arranged for dv by dt, so I didn't have to do any solving. Sometimes you will, and I think we're going to see some examples of that coming up. All right, here's, I'm trying to think, is this one? Yeah, this one's a good one. So, an airplane. You're observing an airplane that's flying at an altitude of 12.5 kilometers. So, let me just reset here so I have lots of space. So there is an altitude of 12.5 kilometers, and I'm a little person somewhere down here on the ground, and there is a little plane. That is the best plane I've ever drawn. A little plane that's flying through the air, and we're going to say that it says flying at an altitude of 12.5 kilometers. I'm just going to say it's always 12.5 kilometers. Plane has reached its cruising speed of 740 kilometers an hour. How fast is the distance between you and the plane changing after 10 minutes? See the problem. There's a problem with this question. 10 minutes after it is passed overhead. All right, so better now. So this plane is going to fly overhead, and actually I'm going to, I'm going to move that so that in my diagram, I kind of am aware that it's going to be directly overhead at time is equal to 0. And then it is going to be further over here. And if I try to understand how that looks, this is how far it is away there, 12.5 kilometers. This is how far it's going to be away from me at some other point in time. And this distance here looks like it's going to be important too. So I could label each one of these distances with a variable if I wanted to. So I could say, for instance, that this is just how far we are apart, so it's d. This one is, I'm going to, just because it's along the x-axis, I'm going to call it x. Now, if I call this y, I don't like to do that because it never changes, and if I can help it, I choose to use just the number instead of a letter when I have constants. Because if I go and set up this equation as a Pythagorean theorem, which you probably see might be a reasonable way to do this, you get x squared plus y squared is equal to d squared. I could call that r probably. That would have been okay. But d squared. I am going to call it r just because a lot of people don't like the dd by dt sort of thing. So I'm going to switch that over to an r. So we get x squared plus y squared is equal to r squared. The problem is that the derivative of y squared is actually 0 because it's a constant. It doesn't change ever. So I would possibly forget that in the middle of the question. So what I suggest as being a really good plan for how to deal with that is to just label that as being the 12.5 because it's constant, never changes. It's 12.5. That's what it always is. So just use the number. All right, so there is this little right angle triangle that's kicking around up here. That color's really nice. I like it. Big fan of purple, though. We're going to switch over to purple. So that's a little diagram. What is it that I know? Well, I know the altitude, and I've labeled that in the diagram. I also know this cruising speed of 140 kilometers an hour. That is how fast it moves through the air. It's moving through the air horizontally. That's the x value. So we know that dx by dt is actually equal to 740. And I'm going to, again, not that it matters because this plane is flying forward and the distance is going to be growing. Sometimes I'm a little over cautious with signs in related rates problems. I'm going to put plus and just say that I'm thinking that it's moving to the right in my diagram. So that is plus 740 kilometers per hour. All right. What we're looking to find is how fast the distance between you, so this would be where I would have had dd by dt. Not that there's anything wrong with that, but dr by dt, it's a little maybe easier to read. And I want to find that specifically when my time is equal to 10 minutes. So that's what I'm looking for. All right, so I want to have an equation that has x and r in it and nothing else if I can help it. And, nothing else variable-wise, which I can make with my diagram. So that is Pythagorean Theorem. So x squared plus 12.5 kilometers squared is equal to r squared. And so when we go ahead and do our derivative with respect to time here, because that's what makes sense, it's how fast things are changing per hour, so it's a time rate of change. So we would have, again, nothing is written in t's, so I have to assume that everything changes not at a rate of 1 kilometer per 1 hour. So if that's the case, then we treat it as a function. The 2 comes down. I leave the inside alone. Now times the derivative of the inside, which is dx by dt, plus 0, because that's just a constant. Doesn't matter what the units are. The derivative of a constant is 0. And then the other side is going to be 2. Leave the inside alone. Now to the power of 1 times the derivative of the inside, which is dr by dt. Great. This was pretty tidy. What are we looking for in the end? dr by dt. So I'm just going to solve, I guess you could say, for the dr by dt. So I'm going to divide both sides by 2. I'm going to divide this r over onto the other side of the equation and say that it's x over r dx by dt is equal to dr by dt. And specifically, if I'm looking to solve for dr, I'm getting really weirded out by how differently I draw my t's and my t's and things. I need to develop a consistency. 36th birthday is coming up. I think if I haven't developed a good, I don't know, good way to go about doing things consistently at this point, it might be too late to teach an old dog new tricks. So make a coffee and let's go. All right, dr by dt. Specifically, when my time is equal to 10 minutes. Now, this is a little bit sketchy because the 10 minutes is not the same time unit as everything else. Well, the one other thing that I've been given in the problem, which is kilometers per hour. I'm going to change my 10 minutes into a time of 1/6 of an hour. Just so that I remember that those don't line up, and now they do. So this is going to be equal to x over r. So the x value at the 10-minute mark, this is what I was talking about in the last problem, which didn't happen there, but I don't have an x value directly given to me. But I do know that at the 0-minute mark, I am right here at an x of 0. And then 10 minutes have passed, which is 1/6 of an hour. And so it's 740 kilometers an hour. 1/6 of the 740. I'm gonna do it on a calculator here. So 740 divided by anyway. So 123.3. So that is Do you know what? I'm actually, just for the time being, just in case it works out a little bit nicer, I'm going to just put that as being 740 divided by 6, unreduced fraction, and I'll tidy it up at the end. So that would be my x value, specifically at 1/6 of an hour past the start. So this thing right here is not everything, even though it's written in a fraction form. That is just my x. So we still have that this is over top of r. And my r is going to be kind of done in a similar way. So if I go up to here, I know that at this 10-minute mark, I guess you could say, that we have, it's true that x squared plus 12.5 squared is equal to r squared, and we know that the x, we just wrote that down, is 740 divided by 6. So 740 divided by 6 squared plus 12.5 squared is equal to r squared. Now, I don't want to deal with the fractions being that large. I'm just going to use rounded decimals. So 740 divided by 6 squared plus 12.5 squared, and then we take the square root of that. So we're going to get 123.96. I'm going to actually probably round that to 124, but I'll do 965, so I'll just do it to the hundreds place for now. So this is, if I follow my units through, this is in kilometers, this is in kilometers, so they're in kilometers squared. You can add together kilometers squared, that's fine. We get that, and then we take the square root of that, so you're going to go back to kilometers. So that is 123.97 kilometers. So that's 123.97. So this is kilometers divided by kilometers, actually, for this first part. And then we're going to multiply this by 740 kilometers per hour. So actually the kilometers here and the kilometers here are going to cancel each other out unit-wise. Let me just go ahead and 740 divided by 6 divided by 12.97. Oops, not 12.97, 123. I was like, this should be really close to 1. And I'll explain a little bit of why that may be the case. So this is going to give me 0.995. You know, the 10 minutes was probably, for the speed of this airplane, it's quite fast. It goes so far, 123 kilometers, that the altitude of 12.5 kilometers is relatively small with respect to both the hypotenuse and the other leg of that triangle, which I'll show you in a moment. So if I take that finally and just multiply it out, I'm going to get that it's 736.2 kilometers per hour. Now, you'll take a look at that and you'll be like, wow, that's pretty much the whole speed. What's really going on there? So once 10 minutes has passed and you have the 12.5 and you have 100 kilometers like this, and you have connected line like this, you know what, let me do the right thing. Let's see how smart is it? Not. All right, well, if I do them one at a time, I think it'll be all right. There, that's pretty nice. So the this side over here, the altitude is going to be fairly small. Now, I mean, I just freehanded this randomly. I didn't do it to scale either, but it's roughly 12.5 versus like 120. Let me actually do that one more time. So 170 divided by 6. This is 123.3, and this is 123.97 or so. 33. So the comparison there is that they're very, very similar. So if this plane flies out a little more this way, it's going to tack on the same amount almost the same amount, because the closer it gets to being like completely flat as it goes out, I guess this way, if you go 1 more meter this way, then this one extends by pretty much 1 meter. And that's almost what's happening at this point. If you had a triangle that looked more like this, then flying out 1 meter more this way is actually, it has a fairly different effect, because the relative size of those are a bit different, quite different. So it's seemingly small, but this would be the correct value for how fast the distance, which is an imaginary thing, but the distance between you, look on the ground, and the plane, the distance between your locations is changing at a rate that's slightly under the actual speed of the plane. So there we go. We can use calculus to get that. Neat little problem that sets up with Pythagorean Theorem. Just be careful of the units, and I don't know, maybe it's just me that feels like sometimes the answer is unsatisfying when it's all really, really close to either like 0 or the original number, but that's not necessarily the case. It doesn't make the problem any less valid. All right, let's do one more, and then I'm going to leave you be to do some practice. Practice makes perfect for this sort of thing. There's all kinds of really cool related rates problems that you can get into, and I'm not even scratching kind of like the surface of what we could do here. So this one says we are walking towards a street light. So here's my little street light, and so bloop bloop doo doo doo, and that street light is 5 meters high, and so we are over here, and this thing is 5 meters tall, and we are walking towards it at a speed of 1.5 meters per second. How fast is your shadow disappearing when you are 10 meters away from the street light? Okay, so first of all, what is a shadow? So a shadow is the lack of a light source being able to reach a certain spot. So if we have a light source up here, so if we were to follow this light ray, it's going to come down like this, and it's going to boom, hit your body. So what would normally happen is that the light ray would be able to extend down here, but it's not able to. So I did that in a little bit of black just to kind of show that that would be shadow created. We would have as well light rays that come down here, of course, and that's not going to have any shadow. So all in here is going to be lit up. And then if we were to skim the top of my head and come over here, then that's going to be lit up all back here too. Because at some point the light kind of like dies off. But basically, all of this is going to be all nice light. And then this little section in here is going to be shadow. So the idea is that there is a length associated with this right here that is the length of my shadow. I'm going to call this distance right here, I'm going to call that X, and I'm just going to call this distance right here for my shadow Y. So I am currently X away from the lamppost, and my shadow has a length of Y. As I walk closer to the lamppost, you can tell that because of the, well, I kind of cut off my head there, because of the angle that the light comes down to be like the last possible, the length of my shadow is going to change compared to what it was out here. So my shadow is actually decreasing. So when it says how fast is your shadow disappearing, that makes sense that it would be disappearing, because as you get really close, it's going to be a very, very short shadow. And right underneath the lamppost there would be no shadow. So the question is, how do we make it so that we could compare the length of that shadow to just other quantities that are given in this question? So it tells us that I am, and I didn't write this down, 1.5 meters tall. Similar triangles are some of the most important geometric relations in these, especially introductory calculus problems. So I'm going to argue that I have a little triangle right here that is going to be one that I know the height of, 1.5, and I know the base of, y. That's similar to a triangle that is like this, that I know the height of, it's 5, and I know the base of is x plus y. So my big triangle, x plus y base, 5 as the, I guess this, my hands are backwards, 5 as the height, and then y is the base, 1.5 is the height. So according to similar triangles, then I can set up ratios that would say 5 divided by x plus y is equal to the height of the smaller triangle divided by the base of the smaller triangle. So I'll make it look like that. I'm going to actually say that 5y then is equal to 1.5x plus 1.5y. I'm getting carried away. What I should have done is something like the following before I do my similar triangles, probably. I should have said, what is it that we know here? 1.5 meters per second is what we are, how our x value is changing, but it's actually a negative because the x is getting smaller. So I'm going to put negative 1.5 meters per second as my dx by dt. Next up, I am looking to find what dy by dt is, specifically when we are 10 meters away from the street light, which is an x of 10 meters. All right, so now I've written down what we know and what we're looking to find. So I want to have an equation that has x's and y's in it. Wow, we have an equation already that has x's and y's in it. Good job, Mr. Reed. So we are going to, you could just take the derivative here, that's fine. But algebraically, we can make this look even simpler. So this is going to be 3.5y is equal to 1.5x. I mean, you can do whatever you want to. You could multiply both sides by 2 if you have an aversion to decimals. Sure, let's do that. So you get 7y is equal to 3x. Or if you like solving for one versus the other, you can have y is equal to 3/7 x. I don't really care. So at this point, all that really matters is we have an equation that has the quantity that we're looking to find, a rate of, which is y, and the quantity that we originally know rate of, which is x. So t derivative of both, no t's here, treat them both as functions. So since it's just y though, it's just the t derivative of y is dy by dt. And constant multiple, that's why I'm leaving that out front, dx by dt. And so I get that dy by dt is equal to 3/7 dx by dt. Specifically, we would like to know the answer when our x value is at 10 meters, which is funny because there is no variable on the right-hand side of the equation. There is no place to put an x is equal to 10 or a y is equal to something or time is equal to something. There's just nothing there. What does that mean? Well, it means that for our problem, no matter where we are walking, the rate of change of the shadow's length is actually also a constant. So if we are walking towards this lamppost, we are walking at a constant rate, so 1.5 meters per second, but the shadow behind us is also decreasing at a rate of 3/7 of 1.5 per second. So meters per second. So what is that? So we get 3 times 3. I think that's good. So 1.5 is 3 halves and 9/14 then. So we would be clicking along, and our shadow is actually decreasing at a rate then of 9/14 of a meter per second. Pretty cool. Pretty cool. And you might say, well, that's smaller. The amount of decrease here is smaller than the amount of decrease in your... Oh, one other thing I should do. I was not careful with signs. So before I talk about that other thing, I need to come back and fix this. So at this point right here, we very early said that this was a decrease, which means that would be negative, which means that this would be negative, which means I can interpret my answer as y, which is the quantity of the shadow's length, is changing at a negative rate. So it is getting smaller, which it should be. So if I'm going to be picky with the signs originally, I should be picky with them as I do the work in the middle, and it will come out the right way. So my apologies for that. But if we look back up the original diagram, basically from here, the person's distance has to become 0 by the time it gets here, and the person's shadow has to become 0 by the time it gets here, but the distance has to be shrinking faster than the shadow, because the shadow has a lot less size than the distance at that point. So during that time, it's got to shrink. I guess we could work out how long is it going to take to shrink at that point. Well, we could calculate it all out, but it should work that they both reach 0 at that same point in time. If we work out how long it's going to take to go from the point when we're 10 meters out to being right underneath, and we compare that to how long the shadow is, we could figure that out by using our similar triangles again at that 10-minute mark. And then looking to see as that decreases whether they both hit 0 at the same time, which I'm sure they will. So that is what I am going to leave it at for now. I think that's a good place to stop. Now we're almost at 50 minutes. Hope that this is helpful to you in understanding how to do related rates. There are a good chunk of questions in the textbook on 255. Do a bunch of them. As many as you can do with still having some fun. I think they're neat problems. You may decide to have a difference of opinion on that, and that would be totally okay. If you come across some interesting ones and you want to go over them with me, I'd love to do that. Just send me off maybe an email. Let me know. I can just I can do 1 or 2 or however many you want. I suppose I could do it in video form like this so that you can see me working on them. I think that's pretty helpful. So hopefully this was good, and miss you, and I hope you're doing well. Take care.